All right, so when we talk about sequences, all we mean by that, it's really just a list of numbers. Any kind of list of numbers. Is what we mean by a sequence. And, of course, a lot of times they're not just random lists. They are some type of pattern to them. 3, 6, 9, 12, 15. And usually the sequences we talk about are infinite sequences. They start somewhere and then they go infinitely, at least in one direction. Yeah, and so here we are talking about multiples of 3. Just a couple of notations. The first term is usually designated with A1. It can vary. We'll vary that some, but general rule of thumb, A1 is the first term. A2, A3, so the A sub n's. A sub n would be the nth term, which brings up another point about it, and that is a lot of times we don't necessarily list the sequence out. We just kind of give it in terms of its generator expression, if you will. So here we could say, well, the nth term is it's a multiple of 3, and so the nth term is just 3 times n, where n starts at 1 and goes by integer. We're talking about integers there. Yeah, so that's, you could also see it sometimes, some places will write a sequence in terms of these little, in these little set braces like this. So that's also generates a sequence. All right, now, as far as graphing these, we may not do a whole lot, but every once in a while we will graph them. But basically, what the difference is between these sequences and a function that we've graphed before is that the domain, if you will, is just 1, 2, 3, 4, 5. Instead of all real numbers, the domain is just starting at 1 and counting numbers or integers. They're up, and so if we graph one of these sequences, well, you're just talking about 1, 2, 3, 4, 5. I can't get out to 5, but we'll stop. But the point I'm making here is, yeah, the graph of these sequences, they're just a series of dots, right? Because at 1 you got 3, at 2 you got 6. There's no in between. 3 you got 9, and so forth and so on. So it's just dots. But the dots, graphing them like that sometimes can be helpful. So just be aware of that. Okay. So let's just look at a couple of sequences here and write out a few terms. I think they usually have us do 5 terms or something like that. A sub n equals 1 over n. And, if you want to write out A1, A2, A3, that's fine, or not. But what would A1 be? It would just be, n is 1, so it would be 1 over 1 is 1. A2 would be 1 over 2. A3, yeah. So you're just plugging in appropriately there. It's a very simple sequence. But compare now the first one we did and this one. Let's look at the graph here, just to kind of get another view of it. A1 is 1, A2 is a half, A3 is a third, a fourth, a fifth. Something like that. This is what I was saying. You can see here that, yeah, this, and probably didn't have to look at the graph, but you can see here that these numbers, of course, are coming in towards 0, aren't they? And so this one converges. You know, we've used that term before. It's the same meaning. So A sub n equals 1 over n. Converges to 0. So that term, it means it goes to a fixed number out towards infinity there. Of course, the A sub n equals 3n. What about that? Does that one converge? Yeah, it just keeps growing infinitely, doesn't it? That one would diverge. So same idea. All right, now, one of the other things that we haven't come across before, I don't believe, is one like this. It's this negative 1 to the nth power. What that does, all right, so A1 here would be negative 1 to the 1 times 1 over 1. So that's going to be negative 1. A sub 2, however, will be negative 1 squared times a half. And so that term is not a negative term because you're squaring the negative 1, makes it a positive 1, so you get a positive a half. And then A3 is negative 1 to the third times 1 over 3. Well, we're back to negative, aren't we? Because you got negative 1 cubed. So you're back to a negative 1/3. And I think you can see the pattern here. If we do 4, we've got negative 1 to the fourth, which is positive 1. So we're back to a positive. Yeah, so I think you can see there what this negative 1 to the nth power does is it just makes us a sequence that has alternating signs. We go from negative to positive, negative, positive, negative. And so, yeah, we haven't dealt with any functions like that before, but now we do, okay? We can have these sequences with alternating signs.
Doesn't that still converge to 0, though?
Yeah, it would still converge, wouldn't it? Because if you look at it, and this is again where the graph does kind of come in handy sometime. All right, so at 1 we're at negative 1, at 2 we're at a half, at 3 we're at negative a third, 4 fourth, 5 is negative fifth, and so yeah, even though they're alternating signs, they're still coming on either side there of 0. So yeah, we would still say those converge to 0. All right. Now, one of the things they have you do on a couple of these homework probably is, so we've got this generator. What's the sequence look like? Well, sometimes they say, here's the sequence. How would you define that in terms of A sub n? So here's one of those. So what's the A sub n right there? Well, like I said, we want to start usually here with n equals 1. And so there's a couple of matters here that we need to talk about. you know, we do have the alternating signs, and so the -1 to a power comes in handy, but is it -1 to the nth power though? Why would -1 to the nth power work here? The first one starts positive, doesn't it? So we'll have to make a little adjustment, and the adjustment is instead of raising it to the nth power, yeah, doing n+1 because, yeah, square that first one. Make it a -1 squared for that first one. And then, of course, the top number is 1. So what about these?
N+2.
Doing n+2? Yeah, they're just going in sequence, aren't they? And so it's almost like 1 over n, but again, make that adjustment because you're starting at 3, and so, yeah. Or something similar to that. Is that okay? Makes sense? All right, here's another one. -1, 1/4, -1/9, 1/16, -1/25. So again, we've got the alternating. We start off with the negative, so just -1 to the end would get it because the first one is negative, so -1 to the 1 would work. All right, now what do we got? Well, we got those denominators again. You just have to kind of look at for patterns. What are these denominators here? Squares, yeah. That's one. You can think of that. I mean, this is 2 squared, 3 squared, 4 squared. You can think of that as 1 square. So yeah, it's just you're just looking for squares or cubes, multiples of 2 would be something else we could look for. But okay. All right. So what about this? 4/5, 9/25, 16 over 125. No alternating sign, so we don't have to do the -1 to the nth thing. But what do you got on the top there?
N+1 squared.
Huh?
N+1 squared.
We got the squares again, don't we? 2 squared, 3 squared, 4 squared. Yeah, the only deal is the first one starts with 4. It's not 1 squared, it's 2 squared. And so to start off the first one with 2 squared, yeah, it'd be n+1 squared. Is that okay? You just got to make that little adjustment because the first one is 2 squared instead of 1 squared. So yeah, n+1 squared. Get it. And what about the denominators there?
5 to the nth power.
You got powers of 5. 5 to the first, 5 to the second, 5 to the third. You got powers of 5 there. And so, and it does start with 5 to the first power, so 5 to the end. Is that what you said? Is that okay? So that's another thing you look for, powers of different numbers. This one was powers of 5. Okay. Now, let's go back and look at a couple of things about converging and diverging. All right. Determine if a sub n equals 7 over n squared divided by n plus 6n squared converges. So yeah, we kind of tackled this. We had some terms, so we looked at the graph and we saw, yeah, those look like they're converged. But how can we do it a little more succinctly, a little more technically, get a little more reasoning behind it here? Well, to be convergent, what that means is I'm looking at, as n goes to infinity, right? I'm looking to see what the numbers go out as n goes to infinity. So am I not looking at the limit as n goes to infinity? And to be convergent, that limit would need to be a number, yeah, instead of infinity or not existing. Yeah, so to determine if a sequence converges, look at its limit as n goes to infinity. So that's just another better way, or more mathematical way, I guess, logical way. All right, so what do we got? We got the limit as n goes to infinity, 7n squared over n plus 6n squared. And we talked about a couple ways of doing this one. You got L'Hopital. The way we did this one back in Calculus 1, actually, and we'll use this technique some other, so might as well go ahead and mention it here. Remember, when n goes to infinity, one technique is to divide by the largest power. So, I mean, L'Hopital, I mean, if you want to do some derivatives, and, you know, depending on the power, though, that might take a while. So I think the better way on these is to go ahead and divide by the largest power. And remember, you do the largest power in the denominator, and in this case it matches the numerator, but even if it didn't, you do the largest power from your denominator. So that's the limit as n goes to infinity, 7 over, and you divide that by n squared, you got 1 over n, and then you divide that by n squared, you get 1 over 6. And remember, when we do that, if we got one of these 1 over n or 1 over n to a power, what happens to that? That goes to 0, yeah. So, yeah. It's a pretty quick way of getting that limit. And so the question was, this converge? And yes, it does. So it converges, and it converges to 7 over 6. All right, how about a sub n equals negative 8 n cubed divided by 9 minus n. So yeah, this is that one convergent. Well, again, if you look at the limit as n goes to infinity, that's what we're interested in here. This one, again, you got a larger power in the numerator, but for our little dividing technique, you divide by the largest power in the denominator. And so we divide the denominator by n, the numerator also, same thing. And that gives us negative 8n squared on top, and then 9 over n minus 1. And yeah, that pretty well lays it out here. So I'd have negative 8 times infinity squared over 0 minus 1. Well, negative 8 times infinity, that'll go to negative infinity. Divide that by negative 1, infinity. So you would get positive infinity out of all that. So not convergent, right? Okay, so being able to recognize those sequences, whether they're convergent and divergent, really when we get going on, because we're going to tie this into series, really we're going to actually want more than convergent. A lot of times we're going to want convergent, not only convergent, but convergent to 0. But that'll come up more later on. Yeah, so let's, one more of these. A sub n equals ln over n. So is that one convergent? Yeah, so this one, just another technique. Limit as n goes to infinity of your a sub n. So yeah, our little divide by the largest power of n here doesn't apply here because you got ln instead of n to a power. But yeah, we mentioned it earlier, but L'Hopital is still at our disposal here because what have we got? Infinity over infinity. As long as you got infinity over infinity or 0 over 0, you can use L'Hopital. So we L'Hopital it. So L'Hopital means do the derivative of the top, which would be 1 over n. Divide that by the do the derivative of the bottom. So we got 1 over n over 1. That's 1 over infinity, which is 0. So that one is convergent to 0. Like I said, that's going to be a good thing when we get to series, to have that thing converge to 0. Not only convergent, but convergent to 0. Just a couple other little terms, and then we'll be done here with this section. A decreasing sequence, just like the name suggests, is decreasing. Each term is smaller than the previous term. To put it into something to check, I guess, if you will. A sub n plus 1 is less than a sub n. The term after a sub n is the a sub n plus 1 term. And so it's less than the a sub n term for, if it's decreasing for everything, it could be for n greater than or equal to 1. A sequence can be partially decreasing. It can, be increasing and then turn into decreasing, just, depending on the function that you've got. But anyway, that's what decreasing means. And a good example is the 1 over n sequence. Increasing also. Same. So example here is a sub n equals 1 over n. An increasing sequence then would be just the flip of that, right? The a sub n plus 1 is greater than the a sub n for your n greater than or equal to 1. An example of that would be some power, number to a power to the n. That one increase it. Well, the one we did, 3n. 3n would be another, increasing one, because the terms just keep getting bigger and bigger. All right, so the other term associated here is monotonic, a monotonic sequence. And it's just kind of a broader category, I guess you will, if you will. If a sequence is either increasing or decreasing, it's called monotonic. So if a sequence is increasing or if it's decreasing, it's called monotonic. So either one of these would be considered a monotonic sequence. If it's decreasing or if it's increasing, it's monotonic. One or the other. So one more here. Is that one monotonic? Well, if it's, if we're asking monotonic, it's either increasing or decreasing. Is it increasing or decreasing?
No.
Why not?
It's alternating.
Down, yeah.
Yeah, if we write out the terms again, well, we got -1, 1/2, -1/3, 1/4. Yeah, from -1 to 1/2, that increases, doesn't it? But from 1/2 to -1/3, that decreases. So it's alternating, isn't it? Yeah. So it's neither one of those. So it's not monotonic. Monotonic just means it's one or the other, but okay. The only other thing I would mention is if you're stuck on whether one increases or decreases, just take a look at this graph. That's one way. So if I have a sub n equals 1 over n squared minus 7n. We could look at, terms, but I mean, we know what a decreasing graph looks like. It's going downhill from left to right. Increasing goes uphill from left to right. So if I just look at this in terms of function, I mean, you don't even have to graph it as a sequence. Just look at it as a graph, because the sequence is just going to be points at the integers there. What does this one look like? I mean, what it looks like. 1 over x squared minus 7x. I have to zoom in a little bit. So yeah, it's got a piece over here, but that's obviously not going to play a role. So it comes up, and I believe it's going to do something. Oh, yeah, it's really got something going on right there as you get out to 7. Yeah, because there's a vertical aspect with 7. Yeah, it looks like, yeah, it's increasing a little while, but then it drops off, and then after that, I'm not even sure what it does. I would guess probably up here. So, I mean, it's definitely not increasing or decreasing exclusively. So, anyway, the graph can bear that out for you too, so I just want to mention that. Any thoughts or concerns there?